Okay, exponential functions. When we're talking about exponential functions, we're going to utilize these for a lot of word problems because they're naturally occurring things in nature and in banking and populations, all that kind of stuff that follows these exponential models. So we have exponential growth and exponential decay. All right, it's going to be growing if things are getting bigger over time, and it's going to be decaying if things are shrinking or getting smaller over time, but it's important that it's going to be a constant percent growth rate every single year or every single month. It's going to be consistent. This is different than linear because remember, linear didn't depend on the previous population or the previous year's amount. It was consistently the exact same change every year. It wasn't a percent. So one big key thing that it's going to be an exponential model is that it's going to have a percent given to us somewhere in the words. All right, another thing that's kind of important on these, as we take a look at them, we can set these up as a times this quantity 1 plus r raised to the x power. Our variable x is going to be up in the exponent on every single one of these. The traditional way to write exponential functions is a times b to the x power, but that corresponds with what we just wrote on the left-hand side because we're going to define b to be 1 plus whatever our rate is. All right, so breaking down the different components here. A is going to be our starting amount, our initial amount. It's what you begin with. R usually comes as a percentage. It can either be percent growth. If things are getting bigger, it'll be positive. Or decay if things are getting smaller, in which case we'll use a negative rate R. Now that comes as a percent typically, but what we want to do is rewrite it as a decimal. So to do that, we're going to move 2 decimal places to the left from where it begins as a percent. All right, B is going to be a growth factor or a growth multiplier. If our rate was negative, then it would be smaller than 1, and things would be getting smaller. If our rate is positive, think about this, our B is going to be bigger than 1, therefore it's going to be growing. All right, let's jump into one of these. So India's population was 1.14 billion in the year 2008 and is growing by about 1.34% each year. We want to write this exponential function to model India's population. And then we're going to predict the population in the year 2020. All right, so identifying a few pieces of information. I know word problems can be challenging, but what we want to do is pick out the numbers. So 1.14 billion. That's what they say we have in 2008. All right, so that's the starting amount. So I'm going to put it in here as a 1.14 billion. And I'm not going to put a bunch of zeros after this or anything like that. I'm simply going to put it in for A, and whatever our answer comes out as is also going to be in billions. Now the other component we need is our rate, R. So our rate is going to be a percentage. It's growing by 1.34%. So 1.34%, but remember we're going to rewrite that as a decimal. So a decimal, you go 2 decimal places to the left. We put a 0 in there. So our rate is going to be 0.0134 gets filled into that formula. And it's positive because things are growing over time. Let's use x as our variable. So our function is going to be f of x equals 1.14 times the quantity 1 plus 0.0134 all raised to the x power. We could simplify this if we wanted to 1.14 times 1.0134 raised to the x power. And you'll see b from up above in this version of the formula would correspond to this 1.0134. All right, now let's try to answer that follow-up question. So that's our model. The follow-up question, kind of a part B on this, is let's use that to predict what's the population going to be in the year 2020. All right, so the initial population was in the year 2008. So if we do 2020 minus 2008, that's going to be 12 years into the future. So our value for x is going to be 12. So let's fill in. We can say f of 12 is going to be 1.14 times 1.0134 raised to the 12th power. Putting that into our calculators, I got this to be right around 1.337, and because our initial population was in billions, this too is going to be in billions. As far as getting this into your calculator, an exponent button is going to be Typically, on most calculators, it looks like this. Up arrow, a caret, sometimes we call it. Other calculators will be like x to the y, or y to the x, or box to the box. Get used to your calculator, though, and get comfortable putting it in, getting the right answers out correctly every time.